Hello and welcome to my quick clip on how to use bond enthalpies to work out enthalpy of reaction. So bond enthalpies are a really useful way and a really easy way of working out the overall enthalpy change of a reaction. Provided you have the right data, in other words the individual average bond enthalpies, for each bond present in your reactants and your products, it's really easy to visualize what bonds are being broken and what bonds are being made. So before going any further and starting to look at a worked example, it's useful to have a quick overview of the information and the ideas you need to have in your head before you start tackling bond enthalpies. So first of all, the bond enthalpy is often referred to as the average bond enthalpy, and it refers to the energy that's transferred when a mole of a certain bond type is broken in the gaseous state. So there's two specific parts to this definition that need to be remembered. It has to be in gaseous conditions, because in liquids or solids you have intermolecular forces that might disrupt or add to the amount of energy it requires to break a certain bond. And in reality, a bond might be formed in a number of different environments, and depending on the environment, you might actually have the effects of other atoms nearby. Let me try and explain. If you take, let's say, a C double bond O, like that, that could be part of a carboxylic acid group. It could be part of carbonyl chloride group, or acyl chloride. It could be part of an amide group, such as that. So in all of these groups, the effects on the carbon double bond oxygen, in other words, specifically the effect on how much energy it takes to break that bond, might be influenced by the presence of the oxygen in the carboxylic acid functional group, or the chlorine in the acyl chloride group, or the nitrogen in the amide functional group. So what we have to do is we have to take an average of the energies that it would take to break the carbon double bond oxygen in a variety of environments. So this is why we call it the average bond enthalpy, as opposed to just bond enthalpy. So let's have an example of this in action. So let's look at three simple examples. Let's make it even more basic than whether there's a chlorine nearby or nitrogen nearby, or whether it's a carbon double bond oxygen. Let's look at the most simple and straightforward and common bond, or two bonds rather, in organic chemistry: carbon-carbon and carbon-hydrogen. If we were to draw methane, you'd obviously have a carbon in the middle, and you'd have four hydrogens around it like so. And each of those hydrogens will be bound to that carbon by a carbon-hydrogen bond, which I'm going to draw in red. If we now move on to ethane, you've got obviously a carbon-carbon bond, and here you've got six hydrogens, each of which is bonded to a carbon. But this is a slightly different environment because of the proximity of the other carbon-hydrogen bonds. So in methane, for example, there's only carbon-hydrogen bonds, and in ethane you have a carbon-carbon bond in the middle. So this one, I'm drawing the carbon-hydrogen bonds in a slightly different colour, which will become apparent in a second, the reason for that. If, let's say, we now go on to talk about propane, obviously, you're going to have three carbons like that. But this time, we have a number of different environments. We have, let me just get the colours here for you. So looking at the three molecules, you'll see that I've chosen a slightly different colour for each slightly different environment. And what I'm going to do underneath the methane, ethane and propane labels is, for each colour, I'll tell you what the bond enthalpy for that particular carbon-hydrogen bond is, because it's in a slightly different environment. So if you follow the colour coding, you can see that there's actually quite a range of different bond enthalpy values, the way that the placement or the environment in which a bond finds itself, even if it's the same bond essentially, can slightly change. I've actually forgotten to give you the value for the carbon-hydrogen bond part of the CH2 group, so I'll just quickly add that in now. So it's interesting to note as well, isn't it, that all of the values are being quoted as positive values. You may recall that when we did this in class, we were talking about exothermic changes being negative delta H values and endothermic changes being positive delta H values. So it's worth remembering that every single bond breakage incurs an energy requirement. It takes energy to break a bond open. That would make sense, because if you think about an elastic band, for example, or a piece of paper or whatever, if you break an object by snapping it, you have to expend energy to do so. So it's no different with chemical bonds, which is precisely what's happening. If you tear a piece of paper, you're breaking chemical bonds, so you're overcoming the chemical energy that's locked up inside it. So a nice way of remembering this is bendo-mexo, or breaking bonds is endothermic, making bonds is exothermic. So it's almost always worth remembering that when we're talking about bond enthalpies. So let's now try this out on a worked example. So this would be a typical A-level exam question, asking you to calculate the delta RH for the reaction of propane with oxygen. You might notice that they've said delta RH and not automatically delta CH, even though obviously this is a combustion. Delta RH can be used to describe any reaction. Combustion is a type of reaction, obviously, so I suppose you could call it delta CH. But if the exam prints it as delta RH, just go with what they say. So you'll notice they've given you a selection of bonds that are present in all of the reactants and products. So what do you do with these? Well, we've already said that bond breaking is endothermic, forgive me, and bond making is exothermic. So to get around that problem, in that exothermic processes tend to be negative and endothermic processes tend to be positive in terms of the values of their delta H's, we use a special equation. It's very easy to remember. I'm just going to put it down here for you. So all you do is to say that the delta RH is equal to the total of all the bonds that are broken. So the bond enthalpies of bonds broken take away the total of the bond enthalpies of the bonds made. So what you've got to do is decide which are the bonds being broken and which are the bonds being made. That's easy, because the reactants have the bonds broken and they're rearranged into the products where the bonds are made. So you can see where I've labelled it up at the top. So what you might want to do is grab a piece of paper and practice this. So thinking about propane, we have C3H8 So I'm actually drawing out the displayed formula of propane so you can see individual bonds. So I'm assuming at this point that what you're doing is drawing this out on a piece of paper, because I'm going to run out of space fairly soon and have to go onto a new slide, which means this will be wiped off the screen. Now, pay close attention to what I do next, because now you have one oxygen, or one O2, another one, and two more. So I'm actually physically drawing out each individual O2 molecule. There's 5 of them, because you can see that from the equation. Now you make 3 carbon dioxides. Carbon dioxide is drawn like that. And you also make 4 waters. So if you remember, water is a nonlinear molecule, so I'm drawing at this slight angle, and I'm drawing 4 of them. And over here the same. Don't worry about lone pairs, we don't need to worry about them at this point, because it's not them we're interested in, it's the bonds. So the next thing I'm going to do is I'm going to label each of those sections with the number of each type of bond from here. So we've got all these bond enthalpies, and what we're going to do is try and assign each of them to the reaction. Okay? So at this point it's worth taking a moment to jot down what all the different bonds are. So in purple at the bottom of the screen, what I've done is I've counted them all up. So you have 8 carbon-hydrogen bonds in propane, that's 8 lots of 413. Remembering that the circled in purple values for all of the bond enthalpies are in the middle of the screen, so 8 lots of 413. You've also got 2 carbon-carbon bonds in the middle of the molecule, that's 2 lots of 347. You then react that with 5 oxygen molecules. All of the oxygen molecules have to be broken apart, so the oxygen atoms can be redistributed. So therefore 5 lots of 498 have to be added. So that's what the bonds that are broken are. So that's all totaled up as the total of bond enthalpies of bonds broken. Now we look at the product side. We've got 3 carbon dioxides. Now 3 carbon dioxides means 6 individual C double bond O's, because if you look carefully, every single CO2 molecule is actually 2 C double bond O's back to back, isn't it? So that's not 3 lots of 805, but 6 lots of 805. And water likewise, each water molecule is actually 2 oxygen-hydrogen bonds back to back. So again, it's 8 lots of OH bonds that are broken here, made, I beg your pardon. So it's 8 lots of 464. So all the C double bond O bonds on the right hand side and the OH bonds on the right hand side are being made, and the C single bond C's, the C single bond H's and the O double bond O's on the left hand side are being broken. So if you want to pause the video, just jot this down, because I'm going to go onto a new screen and do the calculation for you so you can finally see how this technique can give you the delta RH value. So remembering that our calculation said delta RH is going to be the total of bond enthalpies of bonds broken sorry about the writing here. Bonds broken. Take away the total of bond enthalpies of bonds made. So this is not going to win any prizes for neat handwriting. So I admit that straight out. So anyone's watching, please don't make comments about handwriting. I can't help it, it's my iPad pen. It's a bit cheap. So now what we're going to do is put the numbers in. This will allow us to actually do the printing. I'll actually be able to type it a bit better here. So I'll do it one line at a time. So very quickly, I'm just going to label what each of these brackets mean. So the square brackets on the left-hand side is all the bonds being broken. The square brackets on the right-hand side are all the bonds being made. So you can see quite clearly where the numbers come from. Now, remember we talked about Bendel-Mexel. So why am I using positive signs to represent everything when some bonds are being broken and some bonds are being made? When bond breaking is endothermic, bond making is exothermic. Well, the negative sign takes care of that. The fact you're taking the made bonds away from the total of the broken bonds, that deals with that part of the maths for you. So let's look at what this actually gives us. So if you total up all the bonds being broken, it gives you 6488. And you total up all the bonds being made, it gives you 8542. You take 8542 away from 6488, and it actually gives you a calculator value of minus 2054, which is what you'd expect. As it's a combustion, you know that combustions are things burning. When things burn, they give off heat, so it must be exothermic. And that, in a nutshell, folks, is how you do it. It's very straightforward. If you need to go back over any part of this video, please feel free to rewind, or you can obviously email me if you want. My mail address is just coming up. So it's j.o'grady@basvic.ac.uk. Okay, thank you for listening, and best of luck.